What's going on, everyone? Today, I'm going to be teaching you guys logic gates. Pretty exciting stuff. But more importantly, I'm actually going to be teaching you guys the pattern for logic gates, because once you know the pattern, then you'll be able to get all 6 of them, right? So, what you actually have to memorize is the AND gate, as well as the OR gate. Alright, so the AND gate is going to look like the bullet. It's got the nice rounded front end here at the output. And the OR gate is going to look like the skewed bullet. Try and draw that better there. It's going to have an actual point near the output. And again, these are just visual representations of them. It's not actually what they look like. It's all computer circuit stuff, but these are the visual representations of what an AND and an OR gate look like. So let's go back to our truth tables. If you remember those, we need to have 2 inputs and 1 output for every gate. So for our inputs, we'll do 0, 0, 0, 1, 1, 0, and 1, 1. And then on this side will be our outputs. Same thing for the OR gate. Draw our 2 inputs, 0, 0, 0, 1, 1, 0, and 1, 1, and then leave some space for our outputs. So what are the truth table outputs, right? We got to remember that the AND gate is like a series circuit with 2 different switches, and the OR gate is like a parallel circuit with 2 different switches, right? So for a series circuit with 2 switches, it is only going to work if both switches are closed, right? If both switches are 1. If both switches are on, then that's the only way that this whole circuit will be on. Right now you can see they're both off, so we don't have continuity. So same thing with the truth table for the AND. Both inputs are off, the output's going to be off. If one output is off and one input is off and one input is on, like so, well, we still don't have full continuity, so it's still going to be off. Same thing on the other side. If one of them is off but the other one is on, obviously still going to be off. The only way it is going to work is if both switches are on. If both inputs are on, then the output for AND will be on. So your truth table is going to be 0, 0, 0, 1. The OR gate, like I already said, is going to be your parallel circuit, right? As long as one of your switches is on, then you'll have full continuity in the circuit, right? So if both switches are off, like shown right here, you don't have any continuity, so the circuit's going to be off. If one of the switches is on, if one or the other one is on, as long as one of them is on, then you can see that we will have full continuity throughout the circuit as long as we go through this branch. So then it will be on. Same exact thing. If that one's off but this one's on, still have continuity if we go through that branch right there. And then if they're both on, obviously it's going to be on. As long as you can remember these 2 gates, you'll be able to figure out all the rest of them by the pattern I'm about to show you, right? So just remember, the AND gate is like a series circuit, the OR gate is a parallel circuit. So now what are the other ones, right? Well, we have our exclusive OR. Its visual representation of the gate looks exactly like the OR. It's going to have a little pointed end there by the output, 2 inputs, except this X is another little line right there. So it looks exactly like the OR, but it's got 2 little back parts there. Draw that truth table there, 0, 0, 0, 1, 1, 0, 1, 1. And then we also have all of our negation ones. So for every parent, we're going to have a child that's negated. So the AND is going to turn into NAND. The OR is going to turn into NOR, not OR. And then the exclusive OR is going to turn into not exclusive OR, and XOR. Their visual representations also look the exact same. Except since it's negated, N, we're going to have what I like to call our little negation nipple on all these. And that's how you're able to tell the visual representation from the negation to the parent. The N, if it's got the little negation nipple, you know it's going to be negated, either a NAND, a NOR, or a not exclusive OR. Your truth tables for the inputs keep everything consistent here. They're going to look the exact same. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. And again, 0, 0, 0, 1, 1, 0, and 1, 1. So now what are the outputs for the truth tables? It's negated. So everything is going to be completely inverted. So instead of for the AND, our outputs are 0, 0, 0, 1. The negation for the AND, the NAND, is going to be 1, 1, 1, 0. Everything is just the opposite. 0 here, 1 here. 0 here, 1 here, 0 here, 1 here, 1 there, so the 0 goes there. You can do the exact same thing for the OR and the exclusive OR. So 0, 1, 1, 1 will turn into then 1, 0, 0, 0. So now how do we figure out the exclusive OR and the not exclusive OR? These ones are going to be the pattern inside themselves also. Either both of the outsides are going to be the same and the insides are going to be the same, or no, that's for both of them. Both the outsides will be the same and the insides will be the same. It's just a matter of figuring out which one is which. Those will be the same, and those will be the same. So it's either going to be 1, 0, 0, 1 or 0, 1, 1, 0. Well, how do we know? For all of our parents, look at their first output, 0, 0. So we know we can figure out this is what the pattern is, that this first output will also be 0. Since it's not negated, its first output will always be 0. And then, since the exclusive of the pattern, first and last will be the same, so that's going to be the OR, which means these ones are the opposite. It has to be 1, 1. 0, 1, 1, 0. So then we have to completely inverse that for the negation. So in this one, instead of a 0 there, we'll put a 1 there, a 1 there. So we do a 0 there, 0 there, 1 there. It follows our pattern, 1, 0, 0, 1, and it also follows the negation pattern. Our negator there, negator there, negator there, negation nipple, negation nipple, negation nipple, and all the first outputs all start with a 1. Versus our parents up here, like I showed you, all of their first outputs start with a 0. As long as you can remember that pattern, you'll be able to get all the 6 logic gates very easily.